Um, I would also like to start by thanking the organizers. Um, it has been one of the most fascinating weeks, I must say, because I used to think that a lot of my research is about icing, but I didn't know about this whole community of research where I feel like I'm in my first year undergraduate class. So I've learned a lot, so that's my way of thanking you. Thank you very much. I think the projector, yes, this should be okay. Yeah, great. So I'm going to talk about the icing problem as well, but I hope to be able to share with you an alternate line of research where our objective is to first of all study the icing problem or the freezing problem using droplet surface interactions, or a droplet either sitting on a surface or hitting a surface as a model system. And if we cool this system down, obviously we would expect the droplet to freeze, and depending on the kind of dynamics we are introducing, we would think that the phase change process will be interacting with fluid mechanics, and that's what we are trying to look into. I'm an engineer. I'm based in mechanical engineering in UCL. So the engineering objective of our work is to see if we can design surfaces that can hopefully either delay ice formation, or, as it is inevitable because thermodynamically a cold droplet, even though it can exist for a certain amount of time, it's eventually going to freeze. So the thought is, if it freezes on a surface, can we tune the surface properties in a manner that it's easier to remove the ice? So it's passive anti-icing that we are trying to target. And that's where this idea of engineering surfaces at very, very small scale comes into play. So as a first measure, the question is, how does one go about designing a surface that can either delay ice formation or have low adhesion to ice as it forms on it, and so on and so forth? Well, one good place to start would be nature, and it has a lot of nice example of surfaces. This is just one example, very well familiar now, of a lotus leaf which grows without much effort really in tropical climate. It's hard to find here, but the beauty of lotus leaf is if we were to put it under a scanning electron microscope, what you're going to see is this kind of microscale bumps, and if you zoom in even further, you actually see wax nanotubes. So there is this hierarchy of morphology going all the way from microscale, so these bumps are about 10 micrometer, that's the scale here, and these nanotubes on top are much smaller. And these are made out of wax, so hydrophobic. So this combination of low surface energy or hydrophobicity and morphology, it's now begun to be understood, is responsible for extreme water repellency of these surfaces. And the beauty with that is if you can imagine some dust lying on this surface, the water droplet, when it comes in contact, beads up like a mercury droplet, and as it rolls off, it cleans the dust away. So that's what leads to the so-called self-cleaning property. And obviously it has some fascinating application potential. So people have tried to make similar morphologies and hydrophobicities using artificial techniques. This is something where we were using polymers and nanoparticles to spray coat and get this kind of morphology and very high contact angle of droplets. So how does it tie into icing? Well, the idea, at least at the onset, was to use this liquid repellency so that a droplet can roll off quite easily before it has chance to freeze, or even if it freezes, it maintains as little contact as possible, so you have low adhesion, and so on and so forth. So that's what leads to this idea of so-called ice phobicity, so surfaces that are repellent to ice, which delay ice formation or have low adhesion. And I'll also try towards the latter half of my talk show you some results as to how these kind of surfaces can be designed for dynamic anti-icing applications. So where you have a cold droplet hitting a surface. And how do we go about doing that? Obviously, the problem has widespread application. This is one that is closely related to our workshop here, but the dynamic problem also has applications in aerospace and other infrastructure components and so on and so forth. So it's a very active area of research. And I feel like a burden of a community on me because that has not been properly represented. So if I fail, the area still is interesting. I'd encourage you to look into it. There's a lot of fascinating things to be done. We are just starting off there as well. So I think this slide is mainly to try to zone it down a bit in terms of why it's interesting to design hydrophobic surfaces for icing mitigation and passive anti-icing and so on. So what I have here is, imagine a surface, just a flat surface with a liquid droplet, and if I tilt the surface a bit, I'm going to get a bulging of this droplet. So this angle here would be so-called advancing contact angle, and that angle here with the tangent over there would be receding contact angle, because the interface here has to recede if this droplet were to move. And there was this paper about 7 or 8 years ago now who took this as a picture to correlate adhesion of ice with the contact angle of liquid droplets on surfaces. And what they found was, so if you think of this one, this is basically a measure, W is a measure of work of adhesion. So if I separate these two interfaces out, the amount of surface I generate, if I plug in Young's equation, I can calculate this is the amount of energy that I would need to separate this interface, which gives you a measure of adhesion. So what I have here is, according to them, was 1 plus cosine theta of receding angle times the surface energy. This gamma here is nothing but surface tension of the liquid. So cosine is a decreasing function. So if we go all the way from hydrophilic surface where the angle is low to something that is approaching superhydrophobic surface, so let's say 130, 145, if I plug in, I get the adhesion numbers to be 2 orders of magnitude different. And so that gives us a sense of why it may be useful to think about high contact angle surfaces as a useful place to start for anti-icing. So we have surfaces. I showed you, a lot of people have done it, and so had we. And so the thought was, we're going to get extremely low adhesion. We'll solve this problem in one paper. The way I'm pitching it probably gives you an idea that that was obviously not going to be the case. So this is how we started. So this is how our so-called experimental setup looks like. It's a chamber about 1 meter high, in which we have a mini wind tunnel, icing wind tunnel, about a year long, with a fan here, which we could use to blow air on droplets that were sitting on surfaces that we were making. So this is a zoom in of a water droplet sitting on, let's say, one of our superhydrophobic surface. And so what I wanted to do is to start by give you a flavor for how we got into this field. So the experimental conditions are minus 15 degrees centigrade temperature everywhere. We took pains to make sure that was the case. And humidity is relatively dry, about 30% or so. And if we wait long enough, what we are going to see is this droplet is not happy. It's in metastable state at minus 15. It freezes. And it freezes from down here at the interface between the droplet and the solid here. This is heterogeneous nucleation of ice at the interface between our liquid and a foreign object, which happens to be the substrate. If we do the same experiment now with a little bit of airflow from the side, so the droplet is not rolling off, it's still lying on the surface, but we have airflow going from the side like that, what we see is nucleation now starts from the top. Now this is terrible news. Well, first of all, it's good news for us because it gives us something to do and understand, but it's terrible news for people who are trying to design anti-icing surfaces, because surface is out of the picture now. Nucleation is happening in the liquid itself. So the first idea was, well, why is this happening? And what's so different about these two cases? I would like to reassure you, and I can show a number of plots of graphs as to what we did to make sure that everywhere the temperature was very low. And what's happening is relatively simple. So this cartoon is supposed to capture that. And all we have is, even though the temperature everywhere is tried or attempted to be controlled at -15 or whatever it is, the humidity outside is low, so this droplet is evaporating. We feel colder when we sweat, that sort of effect. So the droplet temperature at the top gets ever so slightly lower than everywhere else, and so the homogeneous nucleation becomes more probable. If that were the case, I should be able to show you some complementary experiments to prove that, and I'm going to get to that. But let's just understand this a little bit better. What I'm plotting here is, let's say, energy barrier, free energy barrier of ice nucleation at different temperatures. So this is the picture you should expect. This blue line here is for homogeneous nucleation. The orange line is for heterogeneous nucleation for this sort of contact angle. Approaching 150, which is the threshold for superhydrophobic surfaces. And as we can see, heterogeneous nucleation line is lower than homogeneous one, and that's the reason, as I said in the beginning, we tend to see heterogeneous nucleation more often than not. So what's happening in our case is we have slight decrease in temperature, and you will notice the scale here, it's not too much. So if I plug in the estimate, basic scaling analysis of the temperature decrease at the top, now the top is down here, so the energy barrier is down there, whereas the bottom interface is still up there, and so we tend to see homogeneous nucleation. This is not passive. We've got a parameter here, theta, the contact angle, which we can alter. So if we alter it and we bring it down a bit so that our contact angle is about 130 or so, we can make it such that heterogeneous nucleation becomes favorable again, despite the presence of this evaporation effect. If this were to be true, this is telling us that if you're trying to make anti-icing surfaces, the biggest contact angle is not the best possible option. That's message one. And let's see if this is actually true, if the experiments actually show that. They do, as a matter of fact. So I have here now a series of different surfaces. So this is simple Teflon, non-stick pan, really, where the contact angle is lower, and what you see is, with airflow from the side, dry humidity, nucleation indeed happens from bottom. You go slightly higher, still happens from bottom, heterogeneous nucleation. Go to the other side, very high contact angle. Even if we go to humidity of 70 or 80%, we still see homogeneous nucleation, meaning high contact angles are not good if we have evaporation present. If we kill the evaporation by going to saturated humidity conditions, of course we get back to heterogeneous nucleation again. So this shows us that we are not on wrong track. Okay, so the next thing I wanted to do is to show you, give you a feel for the basics of a freezing droplet, as to what we expect to see, so that we can get some further insight into this evaporation effect. So what I have here is a droplet sitting on a surface where contact angle is just slightly above 90 degrees or so.
How big are these droplets?
So they are about 2.5 millimeters or so. So that's, if they were bigger, they will sag down due to gravity. So the bond number is 0.1 or below. So this experiment essentially is, again, very dry humidity condition, and the temperature in the beginning is at -15, and this is just a cartoon. I can show you the measurements as well, but this shows a better view. And what happens is, if I start this movie up here, what we're going to see is, for a while the droplet is going to stay at -15, and suddenly we will have nucleation event, because this is a metastable state. So we will go into a so-called first stage of recalescent freezing, which is a kinetic effect, and you will see some dramatic effects actually. So suddenly we have a white puff appearing around the droplet, and we'll see in a minute what that is about. And so this stage here, where the temperature rises, because as the droplet is freezing it produces heat, And so we see a very sudden change in temperature to around equilibrium temperature of 0 degrees centigrade. And then gradually this slush that is formed after the first stage freezes in a thermally controlled manner. That's the thermocouple there that I'm measuring the temperature with. It's about 0.25 millimeter in diameter. So we've got the first stage, which is kinetically controlled, and the second stage here, which is much slower, and the freezing is more or less in isothermal conditions. The temperature remains the same. What's interesting is at the end we see a white patch around our droplet, and maybe this is telling us something about the evaporation effect. So let's look at that a little bit closely. So what I have here is now this droplet is put under a microscope from top. This is a substrate, not super hydrophobic or anything, plain piece of acrylic insulated substrate, and we want to see if we see anything around in terms of these white patches and what they are. And what you see is after I start the freezing, you see this nice set of condensate droplets appearing here, and eventually, well, this condensate forms and also evaporates, it turns out, and part of the condensate can touch this original freezing droplet and can form a frozen ring around it. Now let's do the same experiment on copper thermally conducting substrate. We see white patch of condensation around this droplet as well, but it tends to evaporate out. I won't go into the model that we used, very basic diffusion model to understand this. What's happening here is essentially as the original droplet freezes, it releases heat, and that heat gets absorbed by the remaining liquid, which makes it evaporate, because especially when it is lying on an insulating substrate, the heat cannot go through the substrate, and outside we've got air, so it's not a very good heat transfer medium. That means most of the heat gets absorbed by the liquid, so we have vapor formation. Now this vapor is at minus 15 degrees centigrade. It's got nowhere to go but to condense down, and so it does. Now I have the humidity in my chamber down to 1% or so, so that condensate starts to evaporate as well, and some of it can touch the original droplet and form this frozen ring as we are talking about. We call this freezing halo, not my term, somebody else's term, my supervisor in Zurich, but it does look like halo around the droplet, so fair enough. The message here is substrate seems to play a role, and in particular if we are trying to design anti-icing surfaces, thermally conducting substrates might be better, and the reason for that is here. So now we're doing the same set of experiment on acrylic. We've got 3 droplets here. I'm going to touch this one with a speck of ice and start its freezing, and let's pay attention. So we have sudden evaporation after the freezing takes place. Then this guy has his frozen ring around it, which touches the next droplet, initiates its freezing, and so on. In other words, if we imagine a surface with an array of these droplets, if freezing takes place in one of them, if they are sufficiently close, we can have all the droplets in the array freeze. So at least in this controlled condition, we get an insight that thermally conducting substrates or thermally conducting coatings would be better if we are trying to design surfaces for anti-icing application. So that's my message too. Let's go on and try to get some more insight. I was talking about nanoengineering and so on. That's the title of the talk. And so the thought is, let's get into the nucleation process itself. We're by no means the first one to think about it. It has existed for 70 years now, the so-called classic nucleation theory. And there, what you do is, if you imagine bulk cold water and an ice cluster or ice nucleus forming inside it, what you essentially have as drivers in terms of energy balance is this interface between the frozen nucleus and water, as well as the free energy change, the bulk free energy change going from liquid to vapor. So if you do a quick balance of the two, you can calculate the size of ice nucleus that will be thermodynamically stable. And that's what this is about. If we plug the numbers in, it comes to about 2 nanometers at minus 20 centigrade. Okay, just to give you an idea. If you plug that in into calculating the total energy required, this radius into total energy required, we get this sort of a number where we have, of course, the free energy change and the surface energy. So that's for homogeneous nucleation. For heterogeneous nucleation, we get a factor because the ice nucleus has to form on this solid object here, which has, and it forms a contact angle, theta IW, and that comes in terms of this factor. And this factor, as we would expect thermodynamically again, is less than 1. And that's why heterogeneous nucleation is much more probable compared to homogeneous nucleation. The other thing that I'm not showing you here is this radius of curvature here, r, non-dimensionalized here. When it is of the order of this rc, that's when the radius of curvature becomes something that can be used as a tunable parameter. In other words, if we are using surface morphology to control ice formation, our roughness scales needs to be 2 nanometer or within an order of magnitude of that. So we really need precision of surface texture if we want to control ice formation, in addition to the wettability and low adhesion, etc., that we were talking about earlier. And these are one-to-one related to the rate at which this nuclei form as well, as you'd expect from this Arrhenius-like equations. This delta G is the same delta G that we're looking at over there. Okay, so if we need to think about high precision of texture, we have access to microelectronics type fabrication process where we can go and make things with very high precision and surface texture. So this is done on a very smooth silicon wafer where we can controllably achieve roughnesses that are listed here to be able to test that. This is not terribly difficult to do. Everything is controlled here. What's so difficult about it, right? Takes some time. And we can go even further. We can make these surfaces such that we've got micro pillars, and on top of that we've got this nanoscale hair or nanoscale features that I was showing in the last slide. And the benefit here is, if you can imagine a droplet sitting on this surface, is sitting on microscale pillars which have nanoscale roughness on top of it. That means the contact area is really reduced, and in this scale here the droplet is quite big. So we can do we can reduce the surface area of contact quite substantially. The picture is not just as simple. I'll skip some of the detail here. It just turns out that when the ice nucleus forms between these asperities, we've got a layer of so-called quasi-liquid layer as well, and that changes the energy balance a bit, which has significant effect on the way the freezing takes place, for better actually. I'll show you summary result here, which is a result of what are called freezing delay experiments. So in this case, we have these surfaces that we have taken pains and care to make, and we put a number of droplets and we wait till these droplets freeze. When a significant number of them freeze, we count that as the time it took at a particular temperature. So if we go low enough, of course, at a nucleation temperature for this substrate, which is about minus 25 or so, because we've done all that we could to delay the process, it freezes quite quickly. You know, this is 10 to the power of 2 seconds. But if you go just slightly higher, a few degrees higher than that, few degrees higher compared to nucleation temperature, we are still at minus 20 degrees centigrade, and we can achieve very substantial freezing delay. So this is telling us, this is not hypothetical, this is experiment, by the way. So at least in these controlled conditions, we start to gain a sense of how we should go about designing surfaces and how precision is required. It's not just something that we want to do because we can. All right? Right, so in the remaining time that I have, in 10 minutes or so, I wanted to show you a few experiments related to the dynamic effects of droplets hitting a surface. And again, we start with this kind of hierarchical morphology of micro hairs, and on top I've got some nanoscale hairs in order to have as high precision of texture as we possibly can. And what we see if we do droplet impact experiment on these surfaces is, first of all, so this is trying to plot the amount of time that this impacting droplet is spending on the surface. So it comes down, because of inertia it spreads, then the adhesion between the droplet and the solid is very low because we have made the surfaces to be super hydrophobic, so they recoil back and then take off the surface if the impact speed is low enough. And we can characterize the impact in terms of Weber number. So this is inertia, rho v squared, density times velocity. This is, let's say, the size of the droplet, d, and surface tension again. And what we see is, as we lower the temperature, we see an increase, roughly, an increase in the amount of time that the droplet spends on the surface. And the reason for that is, I've noted here, about 5 times increase in the viscosity as we go from 20 degrees centigrade to minus 30 or so that we go down to. I'll show you some details of this mu, n, etc. that I'm noting down here is supposed to indicate the spacing and the diameter of the pillars that I was showing you. If we look at the surfaces from top, I can achieve, and if we imagine a droplet sitting on the surface, I can achieve the same amount of solid liquid contact by varying the diameter of these pillars. So if I use finer pillars and space them closely, I get, let's say, a solid fraction. I make my pillars large and I space them apart, I can get the same amount of solid liquid contact. So in terms of contact area is the same, but in terms of the repellency to liquid, it's a different picture, and that's what I'm going to show you in a minute. The message here is that if we want to avoid icing, we want the droplet to spend as little time on the surface as possible, and because of the viscosity rise, this seems to be critically affected. Surface tension is not influenced that much. Sasha and I were discussing this yesterday, so that's why I noted this one down here. If we are right, we should be able to get similar picture if we were to do these experiments with a fluid where the viscosity is controlled to same value. So that's what we did in this case here, which is a mixture of water and glycerin, and we get the same picture. An insight that I am keen to show to you is something that will become apparent if I get my pointer back today. I probably may not. So let's see. This is a stage where the droplet has just spread out, and the projector is really good. I'm very happy. It never shows up in the other presentations that I make, so kudos to organization. And what we see here is this, I think this is unmistakable, right? We see a ring-like penetration of liquid into the surface texture. I'll show you the pressure peaks in a minute. It's not an accident. That has to do with where the pressure peaks form. The implication of that, though, is quite important, and we see that. So this is trying to plot the diameter of the contact between the droplet and the solid surface with time. As we would expect, as the droplet hits down, it spreads quite rapidly due to inertia, and then the surface energy has to get back, which means that it starts to recoil, and the recoil is slower now because the viscous dissipations have kicked in. And what you see quite dramatically is towards the end stages between the two surfaces that I'm noting here. As I said, they are basically looking at, in terms of solid liquid contact, they are the same, but in one case the pillars are farther apart, and the other case they are closer. And what happens is, when the pillars are closer, you have got higher resistive pressure, capillary pressure, which means that this liquid is finding it hard to get in, which means that it's slowed down to the lesser extent. And you see that in the experiment. These are well and truly beyond the error bars. There's no doubt about that. And we see the same picture in the case of water glycerin as well. So that's an evidence that is the viscosity effect that we were looking at in the previous slide. Okay, so if we get our if we use all that we have learned, we can in fact start to design surfaces that are fairly robust, meaning we can go up to very high speed, high enough for these droplets to come, hit, spread, and fall apart because of the inertia, right? So now in this case we have 5 or 6 meters per second, and the overall picture that is emerging is as the droplet comes down, it has to squeeze out air, it forms this bifurcated pressure peak, which is the reason that the meniscus impales in a ring-like form. So we learned that, and there is a few different pressures that are coming into deciding this balance of whether the droplet is going to get impaled or not. The first one is this capillary pressure, which is related to the curvature, surface tension, and the contact angle, which is resisting the impalement. We would expect the inertia to play a role, but at the low speeds of 10 meters per second or so in this case, it doesn't. The effect that dominates is the compressibility effect. At low speeds is the compressibility of air. If you go to higher speed, you can actually have compressibility of liquid come in, which leads to water hammer effects and so on and so forth. And that's what we are looking at now. So this gives us a nice controlled mechanism of how we should go about designing surfaces. Make the hairs as close as possible, because that way you can control nucleation, make it out of thermally conducting substrate. If it is self-cleaning, so it does not get contaminated, even better, and so on and so forth, right? Everything has been controlled so far. So in last 5 minutes or so, I want to just show you that I'm an engineer. I don't live in the ideal world only. So we are trying desperately to design surfaces with techniques that are scalable. So one of the things that we are trying to do, so here I've plotted the same graph and with the temperature plotted in here. We've looked at this earlier, and what we are trying now is to use techniques such as anodization, which is used in industry quite a lot. And it turns out anodization is basically you've got a metal plate that is maintained as anode, another metal plate that is maintained as cathode. You have an electrochemical bath, and you can create surface nanotexture in plate sizes that fit your bath really. So you are just limited by the size of your bath. Of course, everything has to be controlled in terms of temperature and so on. It's used quite widely in the industry. So the thought is, and this is an example of what we have achieved so far. This is very hydrophobic surface as well, which we reported. And the next step after that is to go towards even finer precision in surface texture. This is made out of aluminium. So I showed you, I told you that other forms of robustness are key as well. So this is a surface where on aluminium we introduced this kind of surface texture by etching, and then we coated them with polymers, and what we showed is that these surfaces are able to take alkaline acidic solution as well as ionic solution. This is supposed to reproduce seawater, 3.5% salt, done in controlled lab conditions, granted. And we see that some of these are beginning to do to have reasonable performance in terms of as far as the laboratory sustainability with respect to chemicals is concerned. Next step after that is if we can think of scaling to even larger areas, so we are not limited to the bath size. So what we did for that is we went back to the original image that I was showing you. We use hydrophobic polymers, we disperse them into solvents, we add some nanoparticles such as carbon black, graphene, carbon nanotubes, which are thermally conducting, to stay true to the idea that we want to make things thermally conducting, as I showed you with some results. And the beauty there is we have a paint suspension that can be spray coated on large areas. So these are some morphology diagrams. This one here is in particular useful, I believe. This is an atomic force microscope image, and this is a profile, and as you can see, these gaps are quite narrow, decidedly designed to be that way, and this has benefit. So if we look at now the maximum speed that we can achieve on these surfaces, we actually cannot achieve it by gravity induced impact. So if you have a droplet which you let go and it can only accelerate by gravity, we very quickly run into terminal speed. So the way around that for experiment is we mix the water with alcohol, a bit of alcohol, which reduces its surface tension, and so we can go to higher Weber numbers of impact. And we can achieve fairly substantial Weber numbers because of that, and that's why you were looking at some of the splashing work. I have some more data which is not published, and we are being recorded here. We can push this quite substantially. So let's say an order of magnitude more. I think I'm allowed to say that by UCL Business. So with that, let me summarize so we have some time for questions. Hopefully, the only thing I wanted to do is to make the case that we've heard enough that icing is complicated. What I wanted to show and add to the forum here is freezing is not just conversion of water to ice. We can have, depending on the ambient conditions, we can have multiple phase change processes happening at the same time. And we must think of all of those for applications where we are thinking of designing surfaces for anti-icing, among other things. I've shared with you whatever we have learned so far in terms of how we go about designing isophobic surfaces, and some ideas around how we can design surfaces for dynamic impact resistance as well as surface design needs and robustness results. Right now, as I said, as I hinted, in terms of future work, we are looking at impacts at higher speeds. At higher speeds, the way we do it is, instead of using water droplet, where we run into the issue of terminal speed, we use water jets, which can be very easily, which can quite easily reach speeds up to 50 meters per second in a lab. And if we change the diameters a bit, we can gain substantial Weber numbers that way. So that's what we're doing now. Next step would be to characterize the adhesion, because that was the motivation, to make sure that it is indeed what we set out to do. And I mean, this is supposed to be not a full stop but a question mark. Sorry about that. And my pitch to the community here is, given what we know and in terms of capabilities that we have, can we use some of this to look at doing some fundamental experiments for ice structure interactions as well? I think there may be some opportunities there. With that, I'd like to thank the people in my current group who have been doing some of the work, and the collaborators, Professor Smith sitting in the audience, and my mentors from the past, and last but not the least, the folks who have been funding and making the work possible. Thank you very much.
Any questions, comments?
Can you comment on possibly existing asymptotic solutions for the problem?
I'd like Professor Smith to talk about it.
And if it
no, I'm not just joking.
Gravity,
Sorry?
If it includes the gravity term.
Yes. Fair enough. Actually, I'm aware of some work. So, in fact, Frank did some work on where they were looking at modeling surface roughness as superposition of Fourier modes on the surfaces, where you can control the amplitude and you can get all kinds of complicated roughness features. Long and short of that is, yes, some of the asymptotics have been done. In freezing conditions, I'm not entirely sure, because you have the complications in terms of whether when a droplet hits down, it freezes upon impact, which is referred as supercooled droplet freezing. Aerospace industry is very worried about that, especially when it comes to large droplets. But what has been observed is these pressure peaks that I was showing, they tend to get attracted towards the surface asperities, which is good for us if we are designing superhydrophobic surfaces, because in the gaps where the penetration is likely to occur, and we want to avoid that, the pressure is somewhat lower and the peaks are sitting at the asperities. That's the extent to which I know. Maybe if Frank has something to add, I'm not sure.
Yes, some theoretical works have been started in recent years for very simple problems. I'll be talking about those in 3 weeks' time at the workshop. No, 4 weeks' time at the workshop.
So that's the invitation to come again.
It's just the beginning.
What
what is the mechanical effect that causes the bounce? You said something about surface energy.
Yes, I did. So if we, this bit is reasonably well understood. So if we think in terms of a droplet, it has got a bit of surface energy, and as it hits down on the surface, it spreads. Its surface energy has increased quite a lot. So it's almost like a stretched elastic sheet which wants to release its energy back. So it wants to recoil back and minimize energy, but it can't do that just as it is because it has viscous dissipation to overcome. So in the beginning you see this inertia dominated spreading, and then as it recoils, the balance switches between surface energy that is getting released as the droplet recoils back and the viscous dissipation. That's at lowish impact speed. If you go to higher impact speed, so when we are hitting Weber numbers of 200 or 300, as this droplet is spreading out, the inertia is just too strong. It causes flashing, which we saw in some of the other higher impact speed droplets.
But the upper particle seems to be narrower than the impact on the downward direction. It splashes out and then comes in, and it's a much thinner column.
Yes, it is.
Yeah.
So we have to. So it's a great question, actually. So if we think in terms of, and as benign as it appears, it's a complex problem as well. So as you're hitting down, the point of impact is your stagnation zone. So there the fluid is stationary. All the momentum is getting released from the edge, and so the liquid sort of folds on itself and goes and becomes a column, and that's why the last bit takes off. Now there has been some work very recently, 2-3 years ago now I believe, that came out in Nature Physics, where they observed something spectacular, where they showed that the droplet hits down, spreads, and then takes off like a pancake. And the reason for that is they were clever enough to design these asperities so that the inertia was not completely killed even in the center. And so in that case you can have pancake bouncing as well.
The question is, what is the minimum size of drops? The minimum size?
So in our experiments we stay around a couple of millimeters, mostly because they're very easy.
But in some cases they are very, very, very small.
True, true. So it's actually a distribution of droplet size, and in particular in aerospace application for cloud droplets, you can have anywhere from a micron or so to about 500 micrometer size droplet. 500 micrometer is already considered as so-called large droplet. And the reason for that is, if you think in terms of aerospace, so I've got an aerofoil and I've got air sheet coming. If the droplet becomes large, it has got its own inertia, so it doesn't follow the aerodynamic drag, which means that as your airstream sort of veers off, the droplet can still go and hit your airfoil and freeze there. So that's why they're terrified of large droplets. But if it is small, it can actually go off, and so on. So depending on the condition, that answers your question. 1 to 500 micrometer in
The
clouds.
question is a little bit other. The ratio between roughness of surface, it is 10 minus h, yes, approximately?
Yes, let's say that, yeah, or 10 minus 7.
And ratio of sizes of droplet and surface, it is?
It's about 10 to the 6, because I'm using 10 to the power minus 3 millimeter size, so it's 10 to the 6. So as far as the scales are concerned, we are still able to use continuum approximation. But I think, as far as I'm aware, Frank's experiments are the first which showed that when you go and look into detailed model, you actually start to see the presence of these asperities and the pressure peaks shift because of that. Peter Hicks from Aberdeen did some work recently as well on that.
Just 2 quick questions. First, thanks for this very interesting lecture.
Thank you. I enjoyed it.
So in one of the first slides, you showed the array of droplets.
Yes, I did. Yeah.
It's sufficiently closed, then the effect will be like spread through
Yeah.
all of them. So what's sufficiently closed?
Great question. So let's see. We've looked at it in excruciating detail, actually. So I won't bore you with the whole thing now, because people are waiting for coffee, I can tell. So let's see. This gives you sort of an idea. So that's where your droplet is. This is the frozen ring. It's approximately 20% extension. Now, it's not as simple as that. So that's if the droplets are too close together, they will be affected. Now, some of this freezing can be happening at fairly low temperature, as we would expect. There, ice can grow at the expense of water because of the diffusion process. So if you have this ring formation, the ring can grow as well. Now, we haven't done the experiment to decide to what extent it does. Thermodynamically it should, and we see that actually in the video that I showed you. Now, granted, I'd like to take a credit that we placed these droplets very precisely so that these two are closer and these two are farther apart, but we just got lucky. Okay, so these are close, so this freezes right after this guy freezes, but here there is some amount of time going on, and the reason for that is what I just told you. Sure.
One question. So could you please suggest some introductory reading on this subject, maybe?
We can't hear the question.
Sure. The question was if I could suggest any introductory reading on this. So there is I can tell you, it's easy to say read my papers. It was too easy. Sorry. So the book by Prof on cloud physics, I think, or Icing in clouds or something like that is the title. It's one of the best. It's a standard text for a long while.
Okay. Last question.
Yes, please.
In a lot of the atmospheric applications, where in terms of the nucleation, what you're actually talking about is kind of like if you have one, there's very few heterogeneous nuclei that you find in particles.
Sure.
And basically, I think people have talked about,
Sure.
Fracturing and splintering, and so you get a cascade of nucleation
Yes.
from that. So, that's sort of another aspect of this is that once you get an ice surface on this,
Yes.
then you're really dealing with impact on an ice surface
Yes.
rather than on the other surface.
That's true.
That's, I'm wondering if you have any thoughts on that and how that.
We do, and as a matter of fact, it gives us a lot of pain to do this kind of control experiments because every once in a while we've got these tiny specks of ice lying around on our surface, and if the droplet touches them, it freezes immediately.
Yeah.
So as far as I'm concerned, the first problem that I introduce in terms of low adhesion is the one that is going to salvage things, because unless we have a nice pristine setup, it's very difficult to imagine a surface which has got no specks of ice so far as real application is concerned. And if you do have a speck of ice, it's as good a nucleation site as any. And so if we did a few basic experiments to show if the droplet as it freezes, it can take off the ice specks and so on, and we have a few neat movies to show off. But you're absolutely spot on. This is one of the biggest concern when designing things for what we are trying to do.
Okay. This is Manish again.
Thank you. Thank you.